Good afternoon, everyone. I'm Manu. I'm a PhD student at Melbourne Uni, and I work with Stuart, Rachel, and Yushan. So as you can see from the title of my presentation, my talk will be basically a cooking class. And the first thing that you need to decide when you want to cook is what you want to cook. Because of course the recipe is going to change if you want to cook butter chicken or pizza or ramen. Well, in my case, I want to cook population 3 stars. So what are population 3 stars? By definition, pop 3 stars are stars with a pristine chemical composition. This means that they have no metals or very little metals. So it means that they're basically done by hydrogen and helium, the only products of Big Bang nucleosynthesis. And from a practical point of view, what you are going to do is to define a critical metallicity, set crit, and all the stars that have a metallicity lower than this value will be pop 3 stars, otherwise will be pop 2 stars. And throughout this work, we will set this critical metallicity to the value of 10 to the minus 4 solar metallicity. So since these stars are the first stars that formed in the universe, they will they will form the first structure that will be realized, so the first dark matter halos that we usually call mini halos. So this is a very simple picture of a dark matter halo that usually surround our galaxy. When we say that a dark matter halo is a mini halo, we usually intend that it has a mass between 10 to the 6 and 10 to the 8 solar masses, so very, very small for being a dark matter halo, since our dark matter halo is about 10 to the 12 solar masses. So the main problem with these stars is that they have never been observed, at least as today, as the 31st of May 2023. I'm not aware of observation of pop 3 stars. So there is a huge uncertainties on their parameters. We don't know what was their initial mass. We don't know how efficient was the pristine gas to be converted into stars. And the only way in which we can tackle this question so far is through simulations. And what simulation tells us? Well, it's generally believed that pop 3 stars were generally more massive, means that they have shorter lifetimes and more likely to end up as a supernova or black holes. And about the gas, it's generally thought that the pristine gas is less efficient to form stars. So the star formation efficiency is lower than what we observe today. Okay, so now we know our ingredient. Now we just have to decide our technique. How are we going to cook our pop 3 stars? Are we going to put it in the oven? Are we going to stir fry it? Well, of course, I'm going to use simulations because there are no observations. So here there is a pretty accurate portrait of myself. And in particular, what I'm going to use is Meraxes with a semi-analytical model of galaxy formation that Balu already introduced, and also Kath mentioned that. So I'm not going to tell much about it, but it's essentially, it starts from an n-body simulation that, for my purposes, is a small box, 10 moving megaparsec on a side, and has a resolution of 10 to the 5 solar masses. This is important because we need to be able to resolve all the mini halos, so all the first structures that we realize. And yeah, so we can resolve every single galaxy, but we are not able to resolve smaller substructures. So basically, our galaxy will either have all pop 3 stars or all pop 2 stars. So this is a simplification that we need to do in our model. And yeah, on top of this embodied simulation, we run all the physics, all the baryonic physics crucial for galaxy formation, from the gas inflow, the cool down, the cooling of the gas, the star formation, and the supernova feedback. In all this framework, what is missing is population 3 stars. So providing a recipe for pop 3 stars basically means updating these prescriptions in order to be able to include the physics of pop 3 stars. This means updating cooling functions, so having new cooling functions for mini halos, because we know that gas cools down differently for smaller halos. We need to add the new properties of star formations. For example, we need to include for the fact that pop 3 stars are probably more massive, but at the same time, when we include these new properties, we want to be a little bit flexible because, as I said before, there is a huge uncertainty on pop 3 star formation. And when we look at supernova feedback, what we are really interested into is the metallicity evolution of the intergalactic medium. Because in order to know if we are forming pop 3 star or pop 2 stars, we need to know what's the metallicity of the gas compared to the critical metallicity. So here's the recipe. Take a high resolution box, at least high enough to resolve the mini halos, add the new cooling functions, keep track of the metallicity of the intergalactic medium, and then mix all together. And when you're forming a POP3 stars, be sure that you are assigned a different property than POP2 stars. Okay, so this is enough was a very long introduction. Now we can start looking a little bit of some preliminary results. So the first thing that I said, POP3 stars are generally more massive. So this means that the initial mass function is usually shifted toward higher masses. And to include this, I took a very simple power law at the initial mass function in a mass range between 1 and 300 solar masses. So we are allowing very massive stars. Here, I'm showing this regime is the regime in which we are forming supernova and black holes. And in this plot, I'm going to show the mass function, so the number of stars per solar mass as a function of mass. Here, since I was saying at the beginning, like there is a huge uncertainty, I'm going to take 3 different choices for IMF. I'm going to take a IMF shifted toward higher masses, so with alpha index of minus 0.5. And another one with a smaller index of equal minus 1.3, so intermediate masses. And then the classic salpeter IMF with an index of 2.3, minus 2.3. So this latter case will basically be, basically say that POP3 stars have the same masses of POP2 stars. Now I'm going to show you as an example, like a few predictions over the cosmic history of our universe, of how this cosmic history changes once we change the 3 different IMFs. So, for example, the first thing that I'm going to show you is the average metallicity of the intergalactic medium. So on the y-axis, we have the metallicity in solar units. On the x-axis, we have the redshift. And the 3 different curves refer to the 3 different IMF. So, and I'm also highlighting the value of the critical metallicity here, 10 to the minus 4. So, as you can see here, the enrichment of the IgM goes faster once we consider high IMF, more massive stars. And this makes sense because more massive stars means more supernova. More supernova means more metals that are ejected. And so that's why in the early evolution of the IgM is very much influenced by the mass of the first stars. While once we go a lower redshift, let's say redshift below 10, the trend is very similar. This is because POP3 stars are probably much less important compared to POP2 stars. Another example of the importance of the initial mass of POP3 stars is given by the star formation rate density. Here I'm showing the star formation rate density in units of solar mass per year per commuting megaparsec cube as a function of redshift. In this case, I'm showing the total star formation rate density with the black line, the POP3 and the POP2 one with blue and red line. And in this case, the impact of the different IMFs is highlighted using different line styles. So the solid line is the high IMF, the dashed line is the intermediate one, and the dotted one is the low IMF. So looking at this plot, you can see that there is not much difference. I agree with you, especially like, let's say, redshift below 18, something like that. The line of the same color superimposed to each other. But what is really interesting here is the very first episodes of star formation, because if we are accounting for a high IMF or intermediate IMF, you can see that the POP2 stars start to form at redshift 23. While if we are considering a salpeter IMF, we can have the first episode of POP2 star formation earlier. And once again, this is a signature of the mechanical feedback of the supernova, because if we have more massive stars, we have more supernova, more gas is ejected. And so like once a galaxy will expel all this gas because of the supernova, it will take a bit of time to recover all the gas, and so to have a second episode of star formation, which will be a POP2 star formation. Okay, so I'm gonna wrap up. So we effectively implemented population 3 star formation in Meraxes, and We did it in a way for which is quite flexible because we can explore different models varying parameters. Here, I show just the IMF, but we can also vary the star formation efficiency for POP3 stars. We did it in a way which is self-consistent, and this is crucial because this allows us to make prediction of the global history of the universe. Here, as an example, I just show the cosmic star formation rate and the metallicity of the intergalactic medium, but there is much more that we can predict. And like, I don't know, like luminosity functions, 21 centimeter signal, 21 centimeter power spectrum, and so on. And all these predictions will probably won't be much affected at redshift closer to a reionization. For me, redshift 6 to 10 is not such a high redshift. When I say high redshift, I mean like really, really high redshift. I'm looking at the cosmic tone. But yeah, so it will be very interesting to apply this model to produce some 21 centimeter global signal and see how this is going to change. Thank you.